My name is Yue, and I'll be presenting our paper, A Cost-Aware Logical Framework, joint work with John Sterling, Harrison Grodin, and Robert Harper. In ordinary type theory, one cannot define a function that associates to a program its computational cost. By definition, this function must assign the same cost to equivalent computations. Therefore, its image is determined by judgmental equivalence classes of terms. For instance, any candidate cost assignment that associates a cost to a Boolean computation takes on the two values induced by true and false, which contradicts our intuitive understanding of cost assignments. The traditional approach to express cost structure in type theory is to consider the cost monad induced by a given monoid. Here, cost-aware programs are tuples consisting of an ordinary program, E, instrumented with a cost component, C. However, there are two problems with this approach. First, it becomes unnatural to express the extensional equality of programs, a problem that becomes amplified at higher types. More nefariously, using cost monads, it is possible to write down cost-aware programs from which one cannot extract an ordinary program. In particular, one may define the following program, which outputs true or false, depending on the cost of the input. We present CAF, a cost-aware logical framework that resolves the aforementioned problems of exposing cost structure in type theory. Instead of the transparent encoding of cost structure via cost monads, in CAF one thinks of cost as an abstract computational effect, which prevents the expression of exotic programs that chooses its output based on the cost component of its input. This synthetic view of cost structure manifests as a call-by-push value language extended with a single effect called step. Indeed, CAF is a dependent version of this language and constitutes a full spectrum dependent type theory for both cost-aware programming and verification. To reason about the behavioral property of programs, CAF is equipped with an extensional phase in which cost structure is trivialized. More specifically, this is achieved by extending the language of contexts with a special proposition called the extensional lock. Intuitively, one may think of the fragment of CAF in which this proposition is in the context as an ordinary extensional type theory. The extensional phase may be internalized as a modality to express extensional properties. For instance, using the extensional modality, one may prove that merge sort and insertion sort are equal extensionally. Crucially, this equality does not hold outside of the extensional phase, which is one of the meta-theorems we prove about CAF. One may be reasonably concerned about how to actually define and analyze algorithms in CAF. Indeed, defining algorithms in type theory is often a cumbersome exercise. On the one hand, most algorithms are defined by general recursion. On the other hand, ordinary type theory only supports structural recursion, which poses a challenge when defining and analyzing algorithms. Our investigations in CAF revealed that one may exploit cost structure to define algorithms, leading to a synergetic situation in which cost structure is used to effectively encode general recursion, which in turn gives rise to efficient algorithms. Using this idea, we study a collection of common algorithms in CAF, including Euclids algorithm, amortized queues, and various sorting algorithms, proving their correctness and verifying their best-known bounds. To hear more about CAF, please come to our talk and read our paper, where you can find out how to define models of CAF, analyze parallel algorithms, and start using CAF yourself. Thank you for watching, and we hope to see you at the talk.